Okay. I think we're good. Welcome, everybody. My name's John Kubiatowicz, but as you heard, everybody calls me Kubi because nobody can actually pronounce my last name. So it's what you get when you take the first four letters of my last name. What I'm going to do today is I'm going to kind of start off the boot camp by giving you a bit of motivation as I knock the microphone off. I'm going to give you a bit of motivation as to why we're here. And to do that, I'm going to start by showing you a bit about, how we got here from an architecture standpoint as a setup for the rest of the boot camp. So in case you're not aware, you've been living in a very parallel world for quite a long time. Okay, from the lowest levels up to the highest level. So at the global level, we've got huge systems in Google and Yahoo and many other large cloud computing providers. And they consist of hundreds and thousands of machines accessible over a network. And at the lowest level, here I'm showing you kind of some research that was at Berkeley a little while ago, a number of years now. Little tiny devices built out of silicon that can walk around. They look kind of like cockroaches. And then everything in between all tied together with a global network. Okay, so this is an explicitly parallel system on the very large scale. So if you didn't realize that, okay, so this is your first thing you learned today. So we're already in a parallel world. Now the question might be, why are people suddenly, as of say 2005 or maybe 2002, as I'll mention in a moment, worried about parallelism? Okay, I worked on parallelism when I was in grad school. You know, it's been around every decade for the last 40 or 50. So what's the deal? And the real interesting fact here is kind of parallelism is forced to be at the lowest level all the time. Okay, that's what's new. You know, we've always had these very large machines with lots of processors on them. It's that down at the lowest level in your cars and your cell phones, you're starting to actually see multiple processors. And that's challenging, as you'll learn throughout the course of these 3 days. So, you know, back in 2007, Intel did a demonstration of concept of a multi-core, although I'd actually call this many-core at this point with 80 chips, or 80 cores in it. But here it is. It's got 80 simple cores tied together with a mesh-like network and 100 million transistors. So this isn't even a big chip by today's standards. More recently, there's another test chip that came out in August of 2010, which was their so-called single-chip cloud computer. And this didn't have quite as many processors. It's only got 48, but it had a more sophisticated uncore, we'll call it, which is kind of the stuff that's around it. All right, so as the demo chips go, so goes the industry, of course. And so as you can imagine, we've kind of been migrating our way along this path for a while now. How many of you have bought a new computer in the last couple of years? Okay, any of you bought that computer with only one core on it? No. Okay. So let's. So that's where we're at. So let's get a little terminology here. When we like to talk about many core rather than multi-core. What's many core? Well, let's say 64 processors, 128. This is not a well-defined term, but let's say 64 certainly cuts it. And how do you program a chip like, say, the one on the left here? Well, you use 2 CPUs for the video and the audio. You use one for word processing, one to browse the web, and 76 of them are virus checkers. Okay, right. Now, hopefully something more interesting can be done with those processors, but if you kind of look at the way a lot of these extra cores are being used today, it's not particularly sophisticated. It's extra daemons in the background or something like that. And so what the PARLAB's all about, as Jim told you, is really trying to use these processors that are available in commodity parts for something more interesting than virus checking, although you can imagine parallel virus checking being an interesting app as well. But I would claim that something else is needed. Okay, and that's really what this course, throughout the course of the 3 days, is really about. So today, my goals in this first lesson here are to pick up some common terminology and concepts for later in the course. I'm going to actually start by tackling uniprocessor parallelism for those of you that haven't taken an architecture course. just so you can see where we've come from and how a lot of these parallel ideas ran out of steam about 2002, but still appear in many different ways. And then we'll talk about parallel computer architecture, okay, which is what you do after you run out of uniprocessor parallelism. And if we have time, which depends on kind of how the course goes here, we'll maybe talk about a zoo of some actual parallel machines or multi-core chips. And what I may do at the very end of the lecture is, well, let's see, we don't have time. Let me show you a couple of cool pictures and we'll look at some multi-core chips and stuff. Okay, so that's probably what will happen at the very end if I have any knowledge of the way this is going to go. So, without further ado, unless there are any questions about where we're going. Incidentally, since we are, over the web here online, when people ask questions, we're going to kind of do one of two things. Either if you raise your hand, we actually have a microphone, and we have somebody who, in sort of Donahue style, can run down and hand you the mic to ask the question, or I will try to repeat your question. But we want to make sure that folks on the web don't get left behind. Okay? All right. So let's talk a little bit about what computer architecture is. So since the 80s, people have clearly understood. It took a little bit of writing to really know what's going on. But to understand that the execution stack is not just about the hardware. So if you kind of look at what happens when you execute something, program, you sort of write the program at a very high level. Maybe you go through a bunch of source-to-source transformations. Some of that work being done in the PARLAB here you'll hear about later. Then you go through a compiler. You probably end up linking some libraries. And then when you're done, you have this thing I'll call an application binary. But that's not even the whole story because it typically dynamically links in library services. There are some OS services. Maybe there's a hypervisor. And somewhere at the very bottom here is the hardware. Okay, so as you can see, hardware here is a very thin slice of what's involved in actually making things work. And there was a time early on in the computer architecture domain where people didn't understand that, and they tried to flatten a whole bunch of this stuff up top down into the hardware, and that wasn't always successful. I like to call this the VAX fallacy. So the idea is you produce one instruction for every high-level concept. Okay, and my favorite high-level instruction was the polynomial multiply instruction, which was a single hardware instruction that took two polynomials described in some fashion, multiplied them together, and produced a third polynomial. Okay? The RISC philosophy was really one of full system design, which is combating what I'd call the VAX fallacy, which was think about the whole stack. Think about what's really matters is the program running, not any of these individual pieces. And the trick is you may want to be able to flatten or flatten out some of these abstractions in places where it makes sense. And so hardware mechanism of the type I'm going to be talking to about in this course here is really in the context of a complete system. It shouldn't be that here we're going to design this cool little hardware bit and hope that a programmer can use it. Okay, and I'll tell you that there's been a lot of computer architecture that has gone that direction. Now, the modern programmer, just to emphasize this, does not see assembly language. Okay, and they probably don't even see C. C is considered sort of an assembly language to a lot of people. Okay, they basically see something much higher level. Okay, which means that the programmer doesn't care what the underlying execution architecture of the hardware really is. Oops, there's some. Anyway, okay, so just to remind you of a few things, how do you not fool yourself? Well, for instance, this is the triangle with the three pieces of the performance. We've got the cycles per instruction, the cycle time, and the instruction count, and it's really the product of those that tells you how long things take. Presumably you've all seen this before, but for instance we have the program can change the instruction count, the compiler can change the instruction count, and maybe the CPI by choosing which instructions. The instruction set can change these things. The organization maybe changes the clock rate, the technology changes the clock rate. And so again, you could easily micro-optimize one of these pieces and end up with a suboptimal solution. The other thing, which is very useful for parallel programming, is Amdahl's law. How many of you have heard of Amdahl's law before? Okay, this is the don't fool yourself in the shower law. Okay, what this says is that your speed up is dependent on what fraction you're actually speeding up, okay? So for instance, it basically says here that the new execution time is what you got with the old execution time times what fraction you're actually enhancing over the speed up, and then there's this piece that doesn't change because you didn't optimize it. So for instance, look at this here. We've got maybe some code down at the bottom with this green piece being some floating point code in the middle of your full application. Here we've sped it up by a factor of 2, and yet the application doesn't speed up by a factor of 2. Right? And even if we sped this guy up by infinite amount, this might get a 2/3 reduction in performance or in time. Okay, so keep that in mind. Right? So for instance, just looking at this, if you're only tackling 50% of your code, the best you can ever do is, for speeding things up, factor of 2. Okay, that's depressing. Right? If you're only tackling 50% of the code, the best you can do is speed the thing up by a factor of 2. Keep that in mind when you think you've got the most amazing optimization ever. Okay, so let's talk a little bit about uniprocessor parallelism. So parallelism, of course, is everywhere. Modern processor chips have of order 1 billion transistors. 1 billion, okay? Not quite the number of our dollars in our federal budget these days, but still pretty large. Clearly, you got to get them working in parallel. If you had all 1 billion of these transistors working in serial, then what's the point? Okay, so the question, the real question is, how much of this parallelism does a programmer actually have to know about? Now, a uniprocessor architect, which by the way, they're a vanishing breed to call yourself solely a uniprocessor architect, extracts parallelism in a couple of ways. One is maybe they find parallelism within an instruction stream. So you, the programmer, wrote this instruction stream, and the uniprocessor computer architect figures ways of picking out some of these instructions that can run in parallel. I'm going to show you that in a moment. This is called instruction-level parallelism, and the theory here is hide everything from the programmer. Okay, and that was a pretty good theory. That worked up until about 2002, where chips just came out. They got a factor of 2 faster every 18 months, and you basically didn't have to worry about it. This was what was great from a programmer standpoint is if your code was too slow, you didn't have to do much work. You just wait for the next generation of processor, and it's fast enough. Okay, I'll let you know now that doesn't happen anymore. Okay, because how many of you, if you've been buying computers and you kind of watch the clock rate, I remember it was amazing, 100 megahertz, gigahertz, 2 gigahertz, 3 gigahertz, 3 gigahertz, 3 gigahertz, and then maybe there's like 3.4 gigahertz or whatever, but things are not speeding up anymore. Okay. So, examples of getting ILP here. Pipelining, basically overlapping individual instruction pieces. Superscalar execution, doing multiple things at once. VLIW is another way of doing multiple things at once, but with a little more compiler involved. Vector processing, specifying groups of similar independent operations that sort of look like vector operations. Out-of-order execution is taking what the programmer said and rearranging it in some way that doesn't violate the data flow path, such that things that are slow aren't holding up things that are fast. Okay, and I'm going to talk about all of these very quickly because obviously that's not the main topic of today, but it's certainly worthwhile. So in talking about pipelining, I love Dave Patterson's analogy of pipelining to doing the laundry, right? And doing the laundry is something we all figured out how to do, hopefully when we were freshmen. But for instance, if you notice here, if you do your loads serially, a wash might take 30 minutes, the dry 40 minutes, folding 20 minutes. It's a 90-minute latency per a load. Okay, but if you pipeline, since you've got a washer and a dryer and a folding table, you can have 3 pipeline stages, okay, and you can go from 6 hours to do 4 loads to a pipelined example of 3.5 hours here. Okay, and notice how we just make sure the washer's always going and the dryer's always going and you're always folding. Okay, it doesn't leave a lot of time to play the, video game on your phone or something, but, it works. And the bandwidth here in number of loads per hour, well, we get 4 loads in 6 hours with the serial example and 4 loads in 3.5 hours with the pipeline example. So this speeds things up quite a bit. Notice that pipelining is helping our bandwidth in loads per hour a lot much, but pretty well, but the latency isn't good. In fact, the latency here went up. Okay, why is that? Because we have slow stages here that stretch out the fast stages. So things get a little slower in total latency, but we get more loads per hour. Okay? And bandwidth is basically limited by the slowest stage, and that's why as an architect you spend all your time balancing stages. Okay, and the potential speed up here is a factor of 3. Okay, simple. Are we good there? Now this kind of parallelism requires me to somehow split tasks up in pieces such that I can have sort of one of each of the stages going at once, and there's no dependencies between stages. Right? So for instance, it isn't the case that I'm trying to fold a sock that's in a later load. Okay, that would be a problem here. Now, here's a 5-stage pipeline, which many of you may be familiar with, but here are the stages: fetch, decode, execute, memory write back, and so we're fetching an instruction while we're decoding, which is also looking up operands for the next instruction while we're executing the previous instruction in memory, look up for the previous instruction, and write back for the very last instruction. Okay, so basically, and as we go this way, we're going earlier in time. So this is the newest, this is the oldest instruction. Okay. There's another way to visualize this, which is a little faster, which is kind of fetch, decode, execute, memory, write back, and you can kind of see the different instructions overlap. So here's instruction 1, 2, 3, 4. Okay. So in the ideal case, we get one new instruction popped in every cycle. So notice how we fetched an instruction here, fetch an instruction here, fetch one, fetch one. So we get a CPI of 1 going and a speed up potentially of 5 here over what it would be if we did each instruction individually. Okay? Superscalar, which is a term you've probably all heard, is basically doing more than one instruction per cycle. So that would be if I fetch 2 instructions, decoded 2 instructions, executes 2 instructions. Okay, is everybody with me on that? All right. Now, what are some limits here? Well, the overheads prevent arbitrary division. So I could imagine taking this pipeline and dividing it into 10 stages, or 20 stages, or 30 stages. The problem, one big problem, is at some point the overhead of the latches here, the green pieces, start becoming of the same order as the thing you're doing. And at that point, it's sort of like pipelining is not buying you anything. Okay, so that's a simple, easy thing to see as a problem. A little trickier are hazards. Okay, and this is where things get a little interesting. So what are hazards? So structural hazards are the easiest thing to think about. So this is the case where you don't have enough of something. Going back to the load analogy, suppose I've got 2 washers but 1 dryer, and suppose the dryer only fits a single washer load. You can imagine I can't get 2 loads going in parallel because there's a bottleneck at the dryer. Okay? Now in modern architecture with 1 billion transistors, structural hazards are easy. You just add more. I don't have enough adders, I'll put another one in. Okay? Data hazards are a little trickier. These are cases where you need a value that isn't ready yet for a new instruction you're trying to start. And I'll show you an example of that in a moment. This one, basically the data hazards, you can't violate the constraints of your program. There's a data flow graph of your program, and the data hazards represent actually getting the result you intend. Finally, there are control hazards, and control hazards are probably the biggest issue in uniprocessor parallelism. A control hazard is a case where I need to make a decision, a branch, true or false, but the decision making for the branch is many pipeline stages ahead yet, hasn't been done, and I have to hurry up and fetch a new instruction. Okay, so a control hazard is a case where I need to make a decision of where to go, but I don't know what to do. Okay. Superscalar, more instructions, gives me more problems with hazards. Okay, more instructions at a time, I have more pressure on the resources. I have more trouble deciding where to go next. So here's a good example, just to give you an idea of hazards. So notice this is an assembly language instruction where I load something from memory and put it in register R1. I use register R1 minus R6 and put it in R4. Here I use R1 minus R7, put it in R6, R1 minus R9, put it in R8. If you look here, this load comes out of the memory stage, And if I line these instructions up like I showed you, notice how it comes out, the load comes out of the memory stage, but it would be needed by the execute stage of the next instruction. So this is actually a back-in-time scenario. All right, and the only way to fix this, actually there's maybe two ways. One is to get faster than light logic, which I haven't known of anybody yet who can get a result out before the inputs are there. If you invent that, tell me about it. The other way is you got to wait. So this guy here has to stall. This instruction has to wait to get that result. Now notice these other ones, I can actually forward from the load stage to this execute stage, or from the register file to this register file. So these two hazards aren't a real problem, but that one's an actual problem. Okay? Are there any questions on hazards? So what we've seen so far is this notion that we got parallelism, we could split things up arbitrarily and try to put multiple things together, but at some point the rubber hits the road and we have to figure out how to meet the real data flow constraints of our program, because it's not useful to do a bunch of stuff in parallel if when you're done you get the wrong answer. Okay, and so making this work, you take a class from me to figure out how to actually make all this work, is what a computer architect would do. They'd figure out how to make these data hazards go away by stalling. Okay, and stalling does what? It slows everything down. So we don't get the parallelism we thought we were getting. Okay? Now, out-of-order execution is another tool that was used a lot. So the idea here is this divide is potentially a very slow instruction. This add is fast, and this subtract is fast. And notice for a moment that this subtract does not depend on the divide at all, or the add. Right? Because the divide puts a result in F0. F0 gets used by this add, but this subtract doesn't use either of them. So the idea behind out-of-order execution would be, well, let's just rearrange these instructions so that there isn't this dependency, and for instance, this subtraction could go faster, start earlier. Okay, and out-of-order execution means that the instructions complete out of order, which is a little tricky. But the trick here is you build hardware, believe it or not, that matches up results with consumers of instructions in a way that still gives you the right answer, even though you're now rearranging the program on the fly in hardware. And an interesting issue, which we won't go into here, is precise exceptions here, or interrupts, which are once I start rearranging the program, if I need to stop on an exception, how do I get a clean state to start over? I mean, because the instructions are executing out of order. It's kind of messy. All right. And then another one here is if the instructions are different lengths and they're executed in different orders, then for instance, this here's a hazard from this multiplier to this divider. I actually have to stall the divide till the multiply is done. Or here's a case where if this add finishes and writes the register back before the divide has read it, then we get messed up. So these are read after write and write after read hazards. Okay, so this is just trying to give you a flavor for the complexity that a computer architect deals with. Simple ideas: pipelining, superscalar, out-of-order execution. Let's see how much of parallelism we can extract under the covers without letting the programmer know about it. Okay. Here's an interesting idea here. Tomasulu came from IBM originally, and the simple idea here is that as instructions come in, they're in a queue. We sort of do a data flow analysis on the fly of figuring out which instructions depend on which. We put them into these reservation stations, and as results finish, they broadcast, and the next instruction that needs a result picks it up and goes. Okay, and so it's sort of, we do this analysis on the fly. We put these in these reservation stations, and the reservation stations are watching results, and when a result comes in, then the instruction fires and we get out of order execution. Okay. So, modern processor. Dynamically scheduled out of order execution. Current microprocessors probably fetch 6 to 8 instructions per cycle. Pipelines are tens of cycles of deep. 20 or 30 cycles is not uncommon, so there's lots of overlapped instructions at once. What happens? Here we go. You ready? This is your big computer architecture all in a single phrase here. Ready? We're going to grab a bunch of instructions, determine all their dependencies, eliminate dependencies whenever possible, throw them all into the execution unit, let each one move forward as its dependencies are resolved, and make sure the result appears as if everything executed sequentially so the programmer doesn't have to worry about it. Got that? Should I repeat it? Oh, maybe not. Okay, so dealing with hazards is challenging here. And what's funny to those who don't study computer architecture is what you end up doing in many cases is you guess. I don't know which way that branch is going to go, so I'm going to guess it goes this way. Fetch a bunch of instructions. I don't know what that value is. I'm going to guess 0. Okay, so the first one's called branch prediction. The second one's called value prediction. And of course, what you do is you arrange so that you can always throw out bad results. That's an important part of guessing because presumably it wouldn't be a guess if it wasn't occasionally wrong. And if you look at modern out-of-order superscalar processors, which you all have in your laptops, and maybe even in your cell phones, although there's less of that there, they're guessing all the time, they're throwing out results. Okay, until eventually they get the right answer. And the one thing to keep in mind about hazards is you can always resolve a hazard by waiting. So if you guess while you don't know an answer and you keep throwing results out, eventually you'll know what the real answer is and you go forward. And the thing to note about this is, of course, and this is where we get into our story for the day, if you're not correct, you throw out results, you're wasting power. Okay, I computed pi to the last digit. Oops, I made a mistake. Throw it out. Okay, I wasted power. And that is really why we start running into problems. And that's where our story kind of really starts today, because the techniques for out-of-order superscalar processors, which really require guessing, got to the point where they couldn't give the programmer this improvement of 2 times every 18 months without ridiculous power consumption. Okay, and that's why it was 100 megahertz, 200 megahertz, 100 gigahertz, 2 gigahertz, 3 gigahertz, 3 gigahertz, 3, because they couldn't improve the clock rate and they couldn't really fetch more instructions, and so the performance just leveled off. And I'm going to show you a graph which makes that really clear. And the other thing to note about it is these processors are complicated. Okay, I know I've simplified it. I'm so amazing. I simplified this that you guys could go and design a superscale processor after today. But there's actually some complexity here, as you might imagine. And these things are not easy to validate and so on. Okay? So let me just show you. Here's an old processor now, but I have a really nice pipeline for it, the Power 4. This is circa about 2000 or 2001. And if you can see here, here's a pipeline for a modern out-of-order processor. Notice how the fetch stage and branch prediction is in a loop all of its own. So it's busy fetching instructions independent of results, including predicting branches. And then, meanwhile, we're shoving instructions down the multiple decode crack stages and so on, where they're taking the instructions, they're decoding them, splitting them into multiple sub-pieces, or regrouping them, all in these sort of pipeline stages. And then eventually we get the mapper stage, which decides when to actually issue the instructions. And then here we get the register file. Remember the 5-stage pipeline, the decode stage was kind of where the register file was really early in the pipeline. Here we are already 10 stages down. And then we do some execution, and at this point we actually figure out whether our branches are right, and we may need to correct things and throw everything that's in these stages out. And what this is actually not quite giving you a handle on is each one of these lines here is actually 2 separate pipelines. So there's really 8 instructions that can be launched at the same time here. Okay? How many people have seen a pipeline like this before? Not too many of you. It's actually, you know, I'm in this field, and whenever I see pipelines like this, you get goosebumps. It's like, oh, that's cool, that works. Okay, and actually it does. But there's a lot of man hours in making things like this work, and things, pipelines have gotten a lot more complicated even since then. But here's the bottom line. Out-of-order execution's not a panacea. Notice this. Here's a graph with a bunch of applications down at the bottom. Okay, we like these kind of things in architecture. And what you see here is 100% of the cycles, and what's black is useful work. Okay, so what's the biggest thing you see here? You see black way at the bottom. Okay, so yeah. So how much useful work is happening? Well, of all of the potential execution, this is sort of 8 instructions that could be launched every cycle in parallel. That would be 100%. Here we're down in the sub 10 to 30%, and 30 is a high one. Okay? What's all this stalling? Well, if you look in here, what you see is you actually analyze things like cache misses, floating point dependencies, lots of data hazards, branch mispredictions. See, here's branch misprediction. All of that stuff in there leads to not really getting what you thought you were with your 8-way issue. Now, for a long time, computer architects were kind of like, well, it doesn't matter. I've got transistors that keep increasing. I've got plenty of power budget, not a big deal. Why not just make things more and more complicated? And yeah, this is not getting the full potential, but it's faster than it was before, so it's okay. All right? What happened? Why did we not continue on this path of, well, it's okay? Anybody know? We don't need a microphone for this. Anybody want to guess? Why did we stop along this path of continuing to make things more complicated? What? So it scales badly, but you know what's funny about scaling is maybe it doesn't matter if I've got enough to scale. Why? Okay, things stop getting faster. I'll agree with that. Does anybody know what one of the big, there's a couple of really big issues that there's a wall that folks ran into. Yeah. Power consumption is a big one. Okay, what else? Heat. Yeah, heat, power, yep. So, interestingly enough, power and energy are kind of two different communities worry about them. They're tightly related, but the power is, gee, it's worried about this thing melting on my lap or in the machine room. Energy is, man, my battery runs down too fast. Those two things are tightly related, but yes, this kind of way of doing things, the energy consumption just went crazy. Anything else? Yeah. Memory. Yeah, the speed of external memory, which unfortunately, behaves according to the laws of physics and therefore can only get so much faster, started to really impact the fact that where pipelines were getting fast. Anything else? Yeah.
Diminishing returns on performance with increases in complexity and man hours that result.
Yeah, completely diminishing returns on, as I throw complexity, you can imagine, you've got, Intel has got architects and they're kind of throwing them against the wall, right? So this is complexity. And at some point, there's diminishing returns in, number of squashed engineers per MIP or something, right? So one thing that surprisingly has never run into problems here is Moore's Law, despite the continual predictions that Moore's Law is dead, has continued. And what is Moore's Law? Well, Moore's Law, I think, is the best story ever. So Gordon Moore, was asked at a conference, what he thought was going to happen for number of transistors on a chip. And like any good academic, he plotted a couple of points on a log linear scale, drew a line and says, it's going to do this. Okay, and of course, when you plot a couple of points on a log linear scale, you get an exponential growth in transistors. Yeah, it's going to do this. And the amusing thing about it is, okay, the slope changed a little, but it did that. And we were basically getting 2x transistors every 1.5 years. And back in 1990, I had somebody who knew a lot who told me that Moore's Law was dead with the next generation. And somewhere around 95, somebody told me Moore's Law was dead with the next generation. And, I've been hearing this every 5 years for a while. Now, there's a good argument that maybe once we hit the size of atoms and so on, maybe Moore's Law's got some problems, but people are looking at lots of interesting techniques to scale, and I think there's good feeling there's a couple of generations of Moore's Law left. So number of parts on the chip is not an issue, okay, and they keep getting smaller, okay? Interesting. Here is the other graph that's more interesting. So this is... people like to call this Moore's Law, but it isn't. This is probably more correctly called Joy's Law, which is the performance of the processor as a function of time. And again, it's on a log linear scale. And for a really nice period from mid-80s up until about 2002, we were getting a doubling in performance every 1.5 years. Okay, and then something happened. Okay? And we've been off that super curve for quite a while. Okay? And what really happened here, and I'll show you some graphs to give you some flavor, all the things you guys brought up, complexity, power, memory wall, and it just all kind of hit the fan on 2002 and things really started going south. And what happened at that point is a bunch of the major manufacturers got together and said, well, you know, it doesn't make any sense to make things faster because it's a ridiculous power budget and so on. Let's just put more of them on the chip because we got plenty of transistors. And in a nutshell, this is why we're in the multi-core era that we're in. Okay, now this doesn't really show you a lot. So one of the things was, I love this graph. This kind of shows that if we were to continue shrinking transistors down the way Moore's law was shrinking them, and we were to continue using them exactly as we had, and we were to follow Moore's law explicitly without changing the architecture, what you kind of see is the density of heat kind of in a point on the chip kind of went from hot plate in the late 90s up until where it would have been about a rocket nozzle worth of heat in 2008 if people had continued along that path. And it's kind of interesting that there's only so much cooling you can do, especially in a portable device. Okay, and if you're following some path, you just can't do this. And here we go. Here's some data which is kind of interesting. So this is from Stanford. It's a really nice graph. I like it. So if you notice here, once again, we've got a linear scale on time and a log scale on numbers of some sort. If we think of those as transistors, notice how the transistor growth is actually following even a little bit superlinear on that scale, so Moore's law is happy. But clock speed is not. So notice, this is the speed of the chips, and here's the 3 gigahertz, 3 gigahertz, 3 gigahertz. And notice how there were even some blips. People went down. So if you notice, there's a bunch of like 2.5 gigahertz chips now, but maybe there are 4 of them. Okay? And also, very little instruction level parallelism left. So it's, I can only take my instructions out, rearrange them, try to launch them in parallel so much, and that kind of ran out of steam. And so this collaboration of things, by the way, this clock rate has a lot to do with power. And actually, here's the power graph too, which I think is telling. I didn't highlight it, but this is the light blue. And notice how it tails off at 100 watts. That's about how much you can easily cool off of a chip without melting a laptop. Okay, this is if we went too much higher on this, laptops would kind of be undesirable, at least for the lab. So there's basically this collaboration of a bunch of things that fell apart, plus the continuing of Moore's law, and that's where people concluded that parallelism must be exposed to the software. We can no longer try to hide it from the programmer because his techniques are just not working. And instead, we're going to make the programmer figure out what the parallelism is and explicitly put it out in sets of chips. Okay? Questions? Good. So you guys are all convinced that uniprocessor parallelism has run out of steam? I hope. You wouldn't be here if you didn't think that. So what do? Well, there are ways of giving parallelism to programmers that aren't so drastic. So one thing, VLIW, was a way of making the hardware simpler. It's called very large instruction word, making the hardware simpler by invoking the compiler a little bit. So we're kind of targeting both the hardware complexity and the power somewhat with VLIW. And the idea is that an instruction word, rather than having a single operation, might have multiple of them. So it might have 2 integer operations, a couple of memory ops, a couple of floating point ops. And the guarantee that the programmer or compiler gives when programming this thing is that, well, the parallelism that's been given here is correct. And you can launch these things in parallel without worrying about getting incorrect results. So none of these things depend on each other. Okay, but notice that we're not figuring that out in hardware. We're figuring it out in the compiler. Okay? And, we could call this a very long instruction word. Intel basically called them packets. Transmeta, they called them molecules. Okay, so there's lots of terms for these things, but these are explicitly parallel chunks of work given out by the programmer or compiler. And each operation slot has a fixed function and timing, and so it's easier. And so the compiler has to guarantee that there are no data hazards, for instance, because if there are data hazards, the architecture will happily compute the wrong answer. Okay? And so you got to have special compiler support to extract parallelism, prevent hazards, and so on. Here's a good example. Here's a serial loop, load, add, store, and we're doing this on a vector of resources. And so basically with every loop, we're kind of subtracting 1 or 8 because we're doing double words from a count, and basically we're working on a vector of double words. Okay? And what we could do in a VLIW here is notice how I can do a load here, which then gets an add 2 cycles later, which then produces a result 3 cycles later. Well, this particular thing has to be guaranteed by the compiler. So this load, we know we put it 2 cycles before this add so that the result will be ready. Okay, and if the compiler arranges these things the wrong way, we get the wrong answer. Okay, and so here's an example of unrolling, which basically gives us a faster result, but notice the holes. What's more interesting about this slide is not where the instructions are, but where they aren't. Okay, and so one of the biggest issues with the early versions of VLIW was code density was really low. There's a lot of empty no-ops in there. And part of the way people fixed these ideas was allowing the long word to be split into packets. That was kind of Intel's idea and so on. But fundamentally, there's a code density issue here. And here's a fun one which I do in my actual architecture class, but we can also use software pipelining ideas. And so here's a case where we do a load, we go around once, we do the add, we go around once, we do the store, and it turns out that this arrangement here actually computes the same answer quite efficiently. It's got 9 unrolled loops. So anyway, you guys all caught that, right? So what else can we do? Well, we could use vectors. Okay, so vectors are another popular idea here. So here we have code that does a loop where we add A of I and B of I and get C of I. And so if you know anything about vector code, you look at this and you say, gee, what's great is none of the iterations depend on each other. Right? And so in the scalar code, this is a mess, right? Because we got to do 2 loads, add, store, but then we do a bunch of updates to indices to sort of work our way through the 3 vectors, and then we loop, and we keep doing that. Okay? And what's interesting there is think about that middle box with what I told you at the beginning of this lecture. What would an out-of-order superscalar processor have to do with that? It'd have to get all of these instructions in the pipeline so they could be reordered for the things that could go in parallel. And this branch, we'd want to be predicting branches enough iterations ahead that we could get multiple loads and adds and stores in the pipeline so that everything's happening in parallel. So a lot of hardware involved just in extracting parallelism out of this code, which we know is parallel. See, this is the funny thing. If you're not a hardware architect where you're sort of enamored with, isn't that cool? You look at this and you say, isn't that stupid? Right? Why should I take this, compile it into this, and make the hardware figure it out? Okay? And in fact, if you have a vector processor, you don't have to. You sort of say, well, there's the vector length register has 64 elements. I load vector V1 from address R1, I load vector V2 from address R2, I do the add of vector 1 and 2 and put it in 3, and I store vector V3 at R3, and I'm done. Okay? But notice, clearly the compiler has to figure out that this can be done in parallel and translate into the right vector code. And amazingly enough, a whole bunch of modern applications, multimedia, HPC apps, etc., that people care about are natural consumers of vector processing. Okay, and so if you have a lot of applications that can map this way, why go to the trouble of translating them to scalar code and then have imperfect parallelism extraction? But notice how, by the way, just to keep hammering this point home, at the point that we've done this, we're really forcing the programmer to extract the parallelism or be aware of it somehow so that the hardware can be told about it. This is not blithely writing parallel code, compiling it as blithely writing serial code, compiling it as serial code, and hoping the hardware does the right thing. It's not. Okay. So what is the programming model? Well, in addition to typical scalar registers, we got a bunch of vector registers, where a vector register actually has a whole bunch of individual elements to it. Okay, they're vectors, not surprisingly. Typical machines may have 64 elements in a vector, or 128. Some of the really large supercomputers might actually have had 1,024. Okay, and what these length of this represents is kind of the level of efficiency for vectors. So if you have really long vectors and you have a machine with long physical registers to it, then you've got really high efficiency. The downside, of course, is if you make these vector registers really long and all your code requires short vectors, and you're wasting a lot of hardware. Okay. So the model here, of course, is that the hardware can take two vectors, explicitly do operations on them, and store them back. And of course, there are things like reductions and so on, which aren't quite so parallel, that vector machines support. And you get to talk a lot about those as you go further in the course. But the other big thing about vector machines is the load instructions and store instructions. And the idea here is that rather than relying on caching, which I'm going to say a lot about in our next little transition here after I let you guys have a break, the vector load and store actually hands a pattern to the memory system and says, look, I'm going to want, starting at this base address and with this stride, I'm going to want you to give me back a whole stream of values out of memory. Start at address 10, go every 2, so 10, 12, 14, so on, and hand that back to me as a stream. And the memory systems know how to handle that. They can say, oh, okay, I will schedule everything internally in my DRAMs to hand it back to me at high rate once I sort of hit a latency point. And so the explicitness about the loads and stores are another really big feature about vector architectures. Okay. We can also do some interesting overlaps here. So I'm just going to show you, here's a case where we might have vectors of size 32, so that's 32 dots in an instruction, but the physical set of adders, there's only 8 of them. So the way you do a 32 vector operation is you do 4 times 8. Okay, and if this load feeds into this, multiplies, feeds into this add, then the vector unit can schedule things so that the first 8 go, and then they get forwarded to the multiplier. Well, the second 8 are going, and then the multiplier goes and forwards on to the add unit. And when we're done, we've done our load, multiply, add, and so we get the first 32 elements of our vector, and if our vector is longer, then we can do the next 32 and so on. Okay, and so there's a lot of choices with vector instructions. Once you've exported the vector instructions, we can choose kind of how much hardware to throw at it. We can throw, 124 adders, or we could throw 1 adder. The same code could scale with different performance on that. Okay, all right. Now, the last sort of thing I want to talk about here before our break is CiMD. So, CiMD stands for Single Instruction Multiple Data, and the notion here is basically that we have a bunch of memories which we can think of as distributed amongst processing elements, and what we're going to do is we're going to do the same thing, that's a single instruction, on multiple pieces of data. Okay, and so we have an array controller here that sort of sends out instructions, and each of those instructions gets interpreted by a local processing element memory combination, and they're doing all the same thing. Now, those of you who are astute might say, wait a minute, isn't that a vector unit? Okay, kinda. And the distinction between CiMD and vector is they're kind of duals of each other in some sense. But you can imagine, for instance, if you're doing an image filter, then locality here could represent part of the image, right? And you could be doing some processing around parts of the image, and you're doing exactly the same thing on all the places in the image, and that was an obvious CiMD type operation. Okay? And of course, they've returned to popularity quite a bit recently with GPUs, okay, which you'll hear a lot about later in the course, I think. Before I mention briefly what a GPU is, I want to show you poor man's CiMD. Okay, so when CiMD first showed up with the connection machine and so on, the idea was you built a special machine that had this property that you'd send a single instruction out to the whole machine and be working on local data. What happened is Intel came up with what I'd call a poor man's SIMD, which is, here's a, let's call this a 32-bit word for a moment. And normally what we do is we take two 32-bit words, add them together, and get a 32-bit result, possibly with overflow. The way you get SIMD out of that is you take the 32 bits and you think of it as 4 8-bit bytes, and when you do the add operation, you break the carry chains so that there's no communication between orange and green and red and gray. And now what you've done is instead of adding two 32-bit numbers, you're adding 4 8-bit numbers. Okay? Sort of SIMD, right? PseudosimD. And what's interesting, so the original was called SSE and so on, and we're up to SSE4, and there's a 5, I think, on the way. But so this has gotten more and more sophisticated, so we can do things like have 4 floats or 2 doubles or 16 bytes and lots of operations and so on. And so this is almost, it's a poor man's SIMD. You could almost think of it as a poor man's vector machine, except it's kind of inflexible in that you have to do things in these quanta of whatever chunks the machine happens to be comfortable with. Whereas in a vector machine, you can vary the width quite a bit. Okay. So finally, what's a GPU? So GPU, basically graphics processing unit, has become very popular. Its history is that originally GPUs were special processors that just did graphics. They'd be a separate chip kind of on the side, and the idea there would be they'd draw triangles and do shading and do interesting things on an image. Okay, except that they became more and more general over time, and in 2006, NVIDIA actually introduced a language called CUDA, standing for Compute Unified Device Architecture, which basically allowed you to take this high-powered SIMD processor and do more general type computation on it. All right, and I think there's actually a whole subsection of our bootcamp on GPUs, so I'm not going to go into them in great detail. But individually, each of these processors kind of do SIMD in 16 or 32-bit chunks where all the same things are happening, but then there's multiple processors here that are somewhat independent of each other. And OpenCL is actually kind of a vendor-neutral version of CUDA. And the basic idea behind all of this was take advantage of the GPU's computational performance, which was originally targeted at images, and use it to accelerate kernels that happen to be well matched to SIMD. Okay? And most GPU architectures to date, although there's a lot of work to fix that, still operate in this detached mode. So it's kind of like the GPU is off to the side and the processor has to communicate with it somehow by sending it data, and then it does its computation and the data gets sent back. And that bottleneck is really historical, and it's kind of interesting to see that a lot of the major companies are starting to look at better ways of integrating them so the communication between GPU and CPU is cleaner. Okay? Good. I think that's a good place to break, so let's take a 30-minute break. Okay, while we wait for the rest of the people to come filing in, we had a couple of pretty good questions in cyberspace. I figured I'd give them to you guys too. So one person asked, gee, is instruction-level parallelism now dead? Seems like a reasonable question. The answer to that is no. In fact, what actually happened is people have pushed instruction-level parallelism as far as they can go with it. And so when they put multiple cores on a chip, there's still instruction-level parallelism being extracted. It may not be as much as at the height of instruction-level parallelism, but it's certainly still there. And in fact, if you look at a lot of chips from Intel, kind of in their sort of main multi-core consumer lines, there's definitely both instruction-level parallelism and out-of-order execution going on in an individual core. So that's one thing I wanted to mention. The second thing is, the question was kind of, if out-of-order execution is so expensive, why do it? And that was from the power standpoint. And the answer there is, well, you do get a benefit from it. It's just a question of, cost-benefit analysis. So if you're willing to spend a little extra power, you can get a big benefit from branch prediction and out-of-order execution, where big is, 10 or 20%. You will certainly do that on a desktop or some other machine that's got power. If you're in a cell phone, you might decide not to do out-of-order execution at all, or branch prediction or any of that stuff, perhaps because your energy budget's so tight. So what I didn't want to imply is that just because we've hit the limits on these things, that nobody does instruction-level parallelism and nobody does out-of-order execution. It's more that we need to make choices now, and many processors, having multiple processors in the mix is the primary choice. And the question of what the individual processors look like is a secondary choice. Okay? All right, and actually, because of Amdahl's law, there are parts of your code that perhaps you can't parallelize well, and so you may want to have as big a beefy processor as you possibly can come up with for those parts of the code that don't run in parallel. Okay, so there's a long, extended answer to those two questions. So what I want to do now is, okay, we're stuck with multiple processors. Now what? Well, one of the things we need to do is come up with a user model. And the very first user model of parallelism I'm going to talk about here that's sort of not the simple vector or SIMD approach is thread-level parallelism. And basically, as I've been telling you, ILP exploits implicit parallel operations within code without telling the programmer necessarily about it. Thread-level parallelism, or TLP, is explicitly representing multiple threads of execution. Okay? And the threads can be on single processor or they can be on a multiple processor. And there's really this question of concurrency versus parallelism, which you might or might not have run into. Concurrency is really this process when two tasks can run complete in overlapping time periods. They're concurrent. It doesn't necessarily mean that they're running at the same time, but rather that you have to allow for them to be running kind of overlapping. Parallelism is when the tasks are literally running together. Okay, and this is a distinction that in many cases doesn't change the way you program, because once you've got concurrency, typically you have to start worrying about races and locks and so on anyway. But I thought I'd make sure we understand that. Clearly, when we go to many-core, we're going to deal with parallelism for sure. And our goal here in this next couple of slides is really talking about using multiple instruction streams to improve either the throughput of computers that run many programs or execution time of a multi-threaded program. Okay. So some common notions of thread creation. So here's the co-begin, co-end idea, where you'd actually write co-begin, co-end, and each line in between here represents a job or a task or something that starts running in parallel. And at the end, once you don't go beyond the co-end typically until both jobs are completed, but they're completely running in parallel. Okay, and they can be nested in some languages. Fork join is a pretty common type of parallelism that I'm sure those of you who have dealt with threads at all have run into frequently, which is I'm running along some code, I execute a fork operation, and what happens is during the execution of that fork operation, I give it a job that is now going to run in the background. And often I get a task ID or a thread ID back so that when I'm done with this other job, which is running in the parent, first job's running in the child, then I can join with the thread ID of the child and make sure that I don't go past the join operation until this child is done. Okay, so I'm forking off a bunch of tasks and then I join back together. Okay. Now a future is another type of parallelism that's is kind of interesting. It's very implicit. The idea here is this job is going to return a value, and by putting future around the call, I basically say, well, you could run it in parallel or not. I don't really need to know, but the value that comes back, V, is not just a value. It's a very special token, so that if this job happens to be running in parallel, then when I go to try to use V, if the job isn't completed and the value isn't ready yet, then something happens. I stall. Okay, so notice here, suppose this future is computing some value and then I'm going to use that value in a sum or something. Well, what will happen is when I get to use V, if this job is not yet done, the future will get invoked and I'll stall until the value is done. Okay. And the important thing to note here is I may express threads without them actually being turned into independent computation. So for instance, in this co-begin, co-end case, it could be that these two jobs end up running serially. Or it could be, in this fork join case, this one is more likely to actually have a real thread that starts up. But you could imagine even here where actually the job 1 runs before the fork returns, and then job 2 runs, and then this join is kind of a null operation. Okay, so notice that the programming semantics don't necessarily include whether or not the actual threads are created or not. Okay? And this is important because what often happens when you express code in threads is suppose you want to deal with from 2 to 128 processors. Now what? All right, well, I'd like to generate 128 threads when I have 128 processors. I'd like to generate 2 threads when I've got 2 processors. What some people will do, which isn't always the right thing, is you'll just always generate 128 threads. And on those 2 processors, they'll just be multiplexed with each other. Okay? The problem with that being it's not always that efficient. Okay. So now we've sort of allowed concurrency and potential parallelism into our picture. So POSIX, part of the title of this talk was talking about the POSIX thread scenario here. And it's basically Portable Operating Systems Interface for Unix is what POSIX stands for. And there's a set of threading calls that are pretty standard. So Pthreads for POSIX threads is basically the POSIX threading interface. And it's got system calls for creating and synchronizing threads. It should be pretty uniform across Unix-like OSs. It's also available on some other ones. And Pthreads contains support for creating parallelism, synchronizing, like joins, etc. And there's no explicit communication support, and the reason there isn't is the idea is that shared memory is backing everything. So if I start 2 threads and one of them creates a data structure and passes its address to the other one somehow, then that other one just reads and writes that data structure. There's no actual communication going on, okay, other than memory. All right. So I just wanted, and by the way, as you'll see, if you look through your schedule, Pthreads here are kind of the least sophisticated threading you're going to learn about in this talks or in this course. So I'm just giving you an idea what the programmer could deal with. You'll get much more sophistication as we go on. But here is, for instance, the pthread create signature, and an example here might be pthread create. I give it a thread ID, which I can use for later manipulation, some thread attributes, which are often just defaults. The function that runs, so these are all pointers, by the way, in C, our assembly language we mentioned from earlier, and some arguments. Okay, very simple. And here's an example of using it. So I might have this routine say hello, which says hello world and returns nothing. And then in the main routine here, notice how I have an array of threads. The first thing I go through is I go through and I create 16 threads. I keep track of their thread IDs in this array. And I use the say hello function as the thing that gets forked off. So now I've forked off 16 copies of something that says hello. And then I go through here and I do thread join on each of the threads in turn, and so I won't actually exit this loop until all the 16 hello threads are done, and then I return. Okay, so this is in C. It's fairly straightforward, and you can get this on most variants of Unix and other operating systems pretty simply. Okay, and what I'm showing you here is the most primitive form of expressing parallelism in a program. Now, variables declared outside a main are shared in this case. Objects associated on the heap, allocated on the heap, may be shared. Variables on the stack are private. Okay, and if you actually pass pointers to stack variables between threads, you're likely to get very weird behavior, so don't do that. And, for instance, we might create a big data structure. Here's a message, hello world, and then when we go to create threads later, we actually pass that data structure in to each new thread, and so this global data structure is used by all the threads. Okay, so very simple shared memory. Okay, questions? Yes?
You mentioned some primitives, co-begin, co-end, future.
Yes.
Are they primitives of some particular language?
Yeah, so the question was, the various primitives, co-begin, co-end, future, etc., are they primitives of a particular language? Yes. So you'd have to find particular languages. I'm just trying to give you flavors of
This is, I cannot say it's part of that language, or it's...
well, for instance, futures, you can get those in several different languages. Things like Silk almost has a future-like syntax to them. Co-begin and co-end, I'm trying to think a good language that has those. Basically, yeah, go ahead.
I just want to throw out that a lot of the primitives are available in library form,
Yeah.
a bunch of languages. So they may be available as primitives in some languages in terms of actual language support, but there's also library support.
That's a good point.
Has very good support C++ for a lot of the primitives.
Yeah, so you can find these as libraries. That's very good too.
I think you also answered my other question. Silk is that what
yeah, it's kind of, well, Silk has this implicit parallelism that might or might not exist kind of view to it, and you'll possibly hear more about that in follow-ons to this. Okay. I'm just going to, the thing is I could go into much more detail on some of these, but I'm just trying to get you a flavor for one of the programmer interfaces. And it is true, especially C++, that was a very good point, has a lot of these things in libraries that you can get a hold of. So that's a good point. Thank you.
And Boost has it.
Yeah.
Okay.
So let's briefly talk a little bit before we sort of end this very simple foray here. So a lot of applications have parallelism. That was our theme. Why make the hardware extracted if the programmer knows it's there already? Here is a common thing that somebody might try to do. They sort of put two levels of loop and they do a thread create for every item. Okay? Now, what's wrong with this? Well, you got to keep in mind that the overhead of thread creation is not trivial. So if this were an array with 1 million elements, this is a very bad thing to do, because you create 1 million threads, you're likely to run tremendously slower than you would if you ever ran on one processor. Okay, so you got to keep in mind that just because you can make threads doesn't mean you should. And in fact, an ideal kind of number of threads per processor is hovering around 1. Okay, if you really like to have efficiency there, you'd like to have 1 thread per processor. Now, you may create slightly more to allow some variation in both the speed at which things are executing and the number of processors you have to deal with, but you'd like to be targeting of order 1 thread per processor. The one exception to that is if you have a lot of concurrency where most of the threads are actually sleeping, and each thread represents something different, some part of the GUI app or whatever, then it makes sense to make a bunch of threads that might be sleeping. But they're not free. Okay? It's kind of interesting. So we're not talking a lot about the PARLAB here. We're giving you sort of a very close segment. But for instance, I work on the operating system portion of the PARLAB. I'm kind of at the operating system hardware interface. And one of the things that we do is we actually have a new ABI that allows user-level construction of schedulers and gives you a much better handle on how many processors you actually have and lets you be able to construct something that goes closer to that order 1 thread per processor kind of thing. But anyway, I just wanted to give you that thing to know. And the other thing to note about is just because, here's an example of maybe a thread creation tree where we have a main threads going through, we create a thread, we create another one, that doesn't necessarily mean anything about when these threads are going to run. Okay, because your scheduler could do anything arbitrarily complicated with it. There's no contract with the programmer that says threads run in a particular order. Any ordering that's required has to be done with locks or some external mechanism. Okay? All right. Now, multitasking operating systems you've been aware of for years now give the illusion that multiple threads happen at the same time, and they do that by multiplexing, right? One thread runs for a little while, then the next one, then the next one, and the next one, and they do that with one processor. And it's typically done at a coarse-grained time quanta for overhead reasons. Hardware multi-threading is an alternative available on some processors, especially today, where the hardware does the switching. So you've all heard of hyperthreads, probably. What's a hyperthread? Well, a hyperthread is something I'll show you much more detail about in a moment, but it's an example of a thread in hardware being multiplexed by the hardware, so that you can actually have two threads and they're not taking the processor at exactly the same time, but the multiplexing is being done in the hardware instead of the operating system. Okay. And when to switch between threads, well, that's an interesting discussion there where you have to trade off kind of overhead of switching and so on and so forth. So the final thing I wanted to talk about in this multi-threading discussion here is what about combining ILP and TLP together? Okay, remember thread level parallelism, ILP is instruction level parallelism. There are different types of parallelism. Okay, ILP is the type of thing you can extract from the instruction stream of a single thread. TLP is you divide the app into multiple independent threads. And so could a processor, for instance, oriented at instruction level ILP benefit from exploiting TLP? You can imagine the answer to that is probably yes. And this is actually called simultaneous multi-threading, and Intel, along with a lot of other companies, never likes to use the original terms for something, so Intel called this hyper-threading, okay, but it was originally called simultaneous multi-threading. And if you remember this graph from earlier, look at this little tiny bit of black at the bottom. We can imagine that there's a bunch of resources wasted because I'm not using them well. Wouldn't it be nice to, in fact, use some of these resources so that we could get black for other threads up into the parts that are idle? Okay? And so here is simultaneous multi-threading where I show my 8-way issue slots, cycle 1, 2, 3, 4, 5, and notice that this yellow thread can only use 2 of my possible functional units here. They can use 3 there, can use a different 2, and so on. Why the white gaps, right? We've done this before today. It doesn't matter what's colored in. Look at the white gaps, right? The reason the white gaps are there are data hazards, branch mispredictions, all sorts of stuff where the unit isn't properly being used. In the case of simultaneous multi-threading or hyper-threading, what we do is we have 2 threads and we sort of fill them in there to make better use of the possible issue slots. Okay, so here's 2 threads, a yellow one and a blue one, and they're making the fact that there's less white and therefore less wasted issue possibility there. Okay. Now, if you look at power 5, remember we showed you 4 earlier. Here's the power 5 diagram, and what they did was they took the power 4 architecture and they added some things here. They have a couple more program counters, a couple more instruction buffers, a little bit more branch history work and return stacks, and some stuff here at the group completion, that's the reordering stuff that happens at the end of an outer order pipeline, and that's it. And as a result, they ended up with 2 threads running simultaneously instead of 1. Okay, so that seems like, that's why hyper-threading has shown up. It's a nice way to sort of better utilize a pipelining. Simultaneous multi-threading, hyper-threading. Why only 2 threads? Well, with 4, then some of this stuff in the middle starts being a bottleneck, and so they basically did that trade-off and decided that 2 was a good idea, and they got 2 threads for only about 24% larger area. So that seems pretty nice. Okay. Now, are there any questions on that part? Yes? So good. So I'll summarize your question there for now. So the question is, in my general rule of 1 thread per processor, am I talking about a hyper-thread / simultaneous thread, whatever, or not? And the answer is, it depends. Okay, so unfortunately there are no absolutes in this story. Why did I say only 1 thread per processor when I said it earlier? Well, because that's a case where if you have too many threads, you're spending all your time switching and you're getting nothing out of it. it could be that if your application has a lot of gaps in here, that 2 threads could actually be better than 1. On the other hand, if your application is less white space and it's doing a really good job of using the processor, 2 threads will actually slow you down a bit. So the answer to your question is, it depends, unfortunately. Okay, but certainly I'm not saying that you want to have 4 or 8 threads in this case. Good. So we have been taking a computer architecture-centric view at the moment here. The other thing that's very important in all of this is the memory system. And this is kind of a very clear graph, I think. So again, we're on log linear scale. That's the only thing we know how to plot in architecture. And what you notice here is that the speed of the CPU was taking up at that, basically factor of 2 every 18 months rate for quite a while. And yeah, it sort of tailed off at 2002. But DRAM has been going at a much slower rate for a very long time. Okay, and there's lots of reasons for this, not the least of which is blasted physics gets in the way. Okay, you got big capacitances and big, you have to communicate over distances in order to make DRAM work. So the problem with this is that this gap between the hunger of the CPU and the ability of the DRAM to feed it has been growing exponentially for decades. All right, so that's a problem. Because your processor, which is doing all these sophisticated out-of-order execution things, or even has more than one processor on it, just can't get enough of the memory system to do a good job. And so what do? Well, we use locality. All right? The principle of locality, of course, is that the program hopefully accesses a relatively small portion of the address space, and therefore we can use caching to do something. And there's 2 types of locality. For those of you that haven't thought about this in a while, there's temporal and spatial locality. Temporal locality basically says if I access something, I'm likely to access it again soon. Spatial locality says that if I access something in a data structure, I'm likely to access something close to it. Okay? And both of these types of locality are important. And I would say the last 25, 30 years, it's only because of locality that computer architecture has made a step forward. And here is an example of something where I've got time along the x-axis. This is address on the y-axis, so this represents which memory location. And if you notice in here, for instance, here is a segment in which the processor is accessing the same address over and over again, so that's temporal locality. Here is an example of spatial locality where the processor is accessing data that's in a range over and over again. Okay, and so this type of caching is really easy. You keep one location around and you overuse it. This is, we take a block of locations and bring them in at a time. Okay? Here is an example with bad locality where I'm just walking through a set of addresses. Okay, and so in that case, caching, this idea of bringing something in to use later, isn't going to help me much, and what really matters there is some form of prefetching. So you have to have hardware that says, oh, I'm going along this set of addresses, let's pull things in. Or, I don't know if you caught that part from an earlier lecture, in the case of a vector machine, I hand the memory system a specification that I'm going to want this stream of things with increasing addresses, and it starts handing them back to me. Okay, so caching's great for these 2 patterns, not so great for here. Vector processing is great for this, or prefetching into a cache might work as well. Okay. So the memory hierarchy, which is a very complex part of a system these days, basically takes advantage of the principle of locality to present as much memory as the cheapest technology and provide access at the speed of the fastest technology. So for instance, here is a processor with some registers. That's the fastest memory. On-chip caches are the next level, fast. Then we might have off-chip caches, DRAM, disk, tape. Oh, you guys forget tape, right? Call that cloud storage, maybe. So what's interesting here is we want to try to present the illusion of the speed of this fastest thing with the size of the biggest thing. And we do that by moving frequently used items closer to us. And that closer could be as much as from disk to memory. That's called paging. Or from DRAM to second-level cache or first-level cache, etc. Okay? Now, here is an example of a Nehalem chip. This one is a few years old now. But notice how it's got 4 cores on it. Okay, those are individual out-of-order processors with, I think they've got two-way issue at least. Here's some, each core has 32K instruction and 32K data cache. It's got a level 2 cache, which is 1 megabyte, and a level 3 cache, which is 8 megabytes shared amongst all cores. So here's the level 3 cache, okay, and there's also some caching inside here somewhere. I think it's right here, which is level 1 and level 2 caches. So what do you gain from this picture, other than the fact that chip plots are kind of cool looking when you look at them? What you see here is there's a lot of area devoted to caching. Okay, and in fact, there's even more control devoted to prefetching and so on. The memory controller is up top here. So what does that say? Well, that says that the only way we're getting performance out of these things is by devoting a lot of work to trying to get by the fact that DRAM is so slow. Okay? And there's an interesting trade-off, which every architect has to think about, which is if I've got a bunch of area, how much do I put for cores? How much do I put for cache? Okay? All right. What's the obvious worry about putting lots of cores on a chip? What do I do with every core? I add more. Well, heat is certainly a worry, but I'm also adding more pressure on the memory system, right? So more cores mean I need more out of my DRAM. So just adding a bunch of cores may or may not help you. So that's an interesting trade-off you probably haven't thought about. You could add a bunch of cores and they could be memory starved and they don't make any progress, and so why bother? Now, obviously there's terminology here. So hit is I find it in the cache successfully. So my hit rate is the frequency of times, or what fraction of time I actually go to cache and get a value. A miss is when I don't hit. Okay, and we have this idea that we're on a miss, we have a miss penalty, which is the time to pull something from the lower level of memory up to the upper levels. And so a miss penalty could be grabbing from the DRAM, it could be grabbing from the third level cache, the second level cache, the first level cache, whatever. Okay? And typical miss penalties can be 500 instructions or more, easily. That's an old number now, it's even worse. So missing in the cache is not a trivial thing. It could actually bring your whole processor to a halt. So what's the impact of the cache on the algorithms? So today, CPU is a function of ops and cache misses. So what does this mean to compilers' data structure? So this is really old data, but I think it's still valid and it's extremely indicative here. So we've got 2 sorting algorithms, quicksort and radix sort. And this is from an old paper now, 97, but I love the result. And if you were sitting down and theoretically analyzing these 2 algorithms, and what you see here is the number of keys I'm sorting on the x-axis, and the y-axis is the amount of time per key. Okay, so an algorithm that scaled perfectly would kind of be flat here somehow, right? And what you notice is theoretically analyzing based on operations, you see that the quicksort starts out great, but then does much worse than the radix sort once you get to a large number of keys. So clearly, if I have a huge database, radix sort is the right thing. Except, you go to do real measurements and you see this instead. So what you see here is the radix sort starts out bad, stays bad, and the quicksort starts out good and gets much worse, but not as bad as the radix sort. Okay, so what's going on here? The person who thought they could just analyze the algorithm from an operations standpoint was confused. Okay, why? Well, look at the cache misses. All right, this is cache miss per key, and what you see here is quicksort starts really low and maybe raises up to 1 or 1.5, and the radix sort starts out with a really high cache miss per key and then kind of stabilizes. And so what you see here is because of the algorithm, it has more cache misses, and that's all the difference here. Okay, so bottom line is you can't ignore the cache when you're thinking about an algorithm. Now, here's another thing that I think is even more amusing. So here's a very simple benchmark that was developed by Kathy Yellick and students. The idea here is I've got a big array in memory, and what I'm going to do is I'm going to walk through the array over and over again. Okay, now first of all, if the array fully fits in cache and I walk over and over again, after the first time through it's in cache, and every subsequent pass through the array is going to be really fast because it's all in cache. Everybody with me on that? So I pull it into cache the first time, but boy, from that point on, really fast. And now what I'm going to do is I'm going to first talk about what happens if this array is too big to fit in cache. So now you can imagine that if I go through it over and over again, I'm going to be cache missing all the time because the later things will kick out the earlier things. The second thing I'm going to do is I'm going to basically sort of say, well, I'll go for every word, and then I'm going to go for every other word, and then every fourth word, and every eighth word. So I'm going to do this algorithm where I skip. Okay, and eventually you can imagine that I skip so that I get the first word and I get the last word, and that's it, because the skip can get that big. And take a look. Here's what we expect. We expect that if things fit in the first level cache, that I'm just going to get fast. This is basically time per access. It's going to be fast. It's going to be at the speed of the cache. On the other hand, if I don't fit in the cache, then what's going to happen is there's going to be a point at the beginning here where every time I hit a new cache line, I'll load the whole cache line, and then I get to access those words quickly. And then I'll go to memory and access the next set of words quickly, and so on, which is why the time for the stride 1 case, where I'm just going every word, is a little bit worse than the cache time, but not too bad. And then as I go bigger and bigger strides, at some point I'm going to hit such that I'm missing every cache line. So I'm going to grab a cache line, and then something will pull in, I'll go to the next cache line, and so on. And so this thing at the top here is the time to go to memory, because every access goes to DRAM. Can anybody tell me what happens down here? Believe it or not, there's an intuition as to why it should fall down again. All right, I'll tell you. So what happens is at some point we're going so far that we are skipping basically so that the subsequent accesses, there's very few of them because I'm skipping very large amount of time. And let's suppose that I only have 4 accesses that I actually make in the whole array. All 4 of them fit in the cache because I have a 4-way set associative cache. And so I get back down to my low point. All right, if you didn't understand that, that's okay. This is simple. Don't you love simple benchmarks? But how does it actually look? Yikes. So here's a real machine. Okay? And what you see here is it varies a lot depending on the array size. And there's no, here's a sort of a good plateau, but it's nothing like that nice clean plateau we showed you. And I can identify things like here is the first level cache time, which basically the small arrays kind of fit well. Here's the second level cache time. So a couple of these plateaus I can identify as points at which things fit in the second level cache. Here's the memory time. This is a 16-byte line, so that's the point at which I'm going every 16 bytes. The second level cache has 64-byte lines, and so on. So I can actually go through here and kind of identify reasons for the deviance. Here is a power 3. All right, what the heck is that? All right, and it's kind of interesting. As the story goes, apparently they actually went to the architects. They said, well, here's this really simple benchmark, and here's this really complex result. Why? I don't know. Okay. So what's the takeaway from this? The takeaway is that modern memory hierarchies are so complicated. Why? Because there's 3 levels of hierarchy. The system's busy trying to prefetch things and figure out what strides are going, and it's basically trying to give you better performance underneath the covers without you worrying about it, and as a result, a simple benchmark has these really weird plateaus in it. Now, you could look at this and say, well, that's fun, but it does, I guess it works. If you're Jim Demo, or Kathy Yellick, or other folks in the PARLAB, you might say, well, wait a minute, what if I want the perfect algorithm for my cache hierarchy? How do I find it? Okay? And the answer is automatically. So the thing I will mention first of all is notice it says caches vastly impact performance. I didn't say improve performance. Okay, impact. Now, of course, they improve performance in a lot of cases, but they vastly impact performance. The actual performance will vary a lot. Okay, slight changes in the architecture or the prefetch algorithm can change the way an algorithm works. All right, and there's some common techniques, by the way, if you were to study. In fact, I think maybe we might even do this in one of our lessons. I'm not sure, but at some point you might encounter the ability to do blocking and tiling. These are ways of rearranging loops to do better with the cache. But at some point, you really need to do what Jim talked about earlier this morning called auto-tuning, which is deal with the complexity through experiments. So in principle, if you're doing something, what you do is you have the ability to have several different variants of the algorithm and several different blocking sizes, and you want to go through the search space and find the one that is the best for each architecture, in principle. And that's because the architectures are so complicated. And there's a whole lecture on that tomorrow, I think, or maybe Wednesday, I don't know. Okay, questions? All right, so yeah, throwing memory hierarchy in the mix, unfortunately. Sorry about that. So now let's migrate on to explicitly parallel computer architecture. So notice that even when I was talking about threading, there wasn't any explicit parallelism there other than the programmer says these things could run concurrently. Okay, let's dive down and see what a parallel architect might worry about. So what is parallel architecture? So a parallel computer is a collection of processing elements that somehow cooperate to solve large problems. And the most important new element in all of this is it's all about the communication. So before, when I actually had the hardware figuring things out for me, I didn't have to worry about how these different parallel instructions communicated with each other. That was all done for me. Now if I've got 64 processors or I have a GPU or something, I actually have to explicitly worry about who communicates with whom. Okay, and can they communicate with each other? So there are some processors that can't always communicate directly. And what does the programmer think about? Well, they think about, maybe models of computation, I don't know, PRAM, BSP, sequential consistency. They may think about allocating resources, like how powerful are the processors, how much memory do I have? The mechanisms might be things like, I don't know, what's the single processor? Well, it might be a high-performance general-purpose processor. It might be a CiMD processor. It might be a vector processor. We have to worry about how do we communicate between them. What's our data access communication and synchronization mechanisms? Okay, these are all things that suddenly are in the mix for the poor programmer since we decided to give up on implicit parallelism. Poof. Welcome to our course. It's a little discouraging, perhaps, because people have been at this for 50 years, and I think they've made a lot of progress. We like to think in the PARLAB we made a lot of progress on how to program these things, but let's face it, a explicitly parallel architecture is much more complicated to program than an old serial architecture. Old, yeah, right, 2002. Okay. So I like to talk about parallelism. So you've kind of seen superscalar here would be multiple things at once with a single thread. So that's kind of here, we have the white space as unused issue slots, but basically we have a single blue thread. We have a couple of multi-threading options. Here's a case where maybe we switch off every cycle between different threads. That's fine grained. Here's a case where maybe we switch off periodically. Okay, I actually built a machine like this a while back where you'd only switch when you, say, had a remote memory access that was long, and so the overhead of switching was okay to be a little larger. We just talked about simultaneous multi-threading. And so in this pantheon of possible parallelism, we actually have multi-processing, right? So here's a case where I've actually divided this into two chunks, and I think implicitly, based on the question basically from cyberspace 2 earlier, was maybe the individual processors are a little simpler than the complex processor might be. And so notice how I'm kind of showing that we're only issuing 2 instructions per cycle. But we have 2 processors. Okay, and so you could actually talk about normalizing the total hardware across these different options and doing trade-offs and so on if you were, say, an architect. Okay? But the point here is this is not to say that we get rid of all ILP or out-of-order execution. You need to look at what the processors are. You buy a Core 7 or 5 or whatever from Intel, you'll get out-of-order execution, multiple issue in each individual processor still. So programming model is kind of made up of the languages and libraries that create the abstract view of the machine. We have to worry about things like how do we create parallelism. I showed you that with Pthreads earlier with some of my thread creation operations, but there are other options. We can ask about what are the orderings between operations. We can ask about how different threads synchronize with one another. Remember we showed you join earlier, which was kind of a coarse grain, wait until that thread is done. But you can imagine if you're really doing a lot of parallelism, you really want the threads to continue and they have periodic synchronization points. Data, we might ask what's private, what's shared, how do we communicate data? Synchronization, what operations can be used to coordinate parallelism, and at some point we kind of say what are the atomic operations here? Okay, there was some mistakes made in early architecture that basically got rid of things like test and set and swap and some of the atomic operations, and you couldn't synchronize. MIPS was a notorious example of that in the early days of microprocessors. And then, of course, we have to ask what's the cost and how do we get performance out of all of this. So here's a simple programming example, which I'm going to take through a couple of things here. So, we got an array A, and we're going to run through and sum f of A over all the elements. Okay, that seems like that could be a useful thing to do on occasion. And so the questions we might ask on a parallel machine, where is A? Is it all on one memory or is it distributed? What does each processor do? Clearly, if we have multiple processors working, they need to coordinate to get the final sum. How does that work? Okay, so here's our array. We apply a function. We get a sum. So I'm going to talk about two possible communication styles, shared memory and message passing here. Those are two pretty good examples of points in the space. So shared memory, first of all. The idea behind shared memory is there is this mysterious big pot of memory in the sky that all processors can access. Okay, so in case you didn't catch it, this is the sky and this is the processors. Right? So the nice thing about shared memory is a processor gets an address, it can write to memory by writing to that address, and this processor can read from memory by reading from the address. So in some sense, as a how far do you have to get out of your comfort zone to program parallel tasks? Shared memory is not very far out of my comfort zone. Right? There's a lot of things that could all be running, but gee, it's just addresses, and anybody can read any address. Okay? Now, the program, therefore, is a collection of threads of control which are actually running in parallel. Each thread is a set of private variables, local stack variables, so on. And then there's a set of shared variables, like static variables, shared common blocks, global heap, and they're all in the shared memory. Now, I haven't showed you how to build this yet, and that's, of course, an interesting issue if you're an architect. We'll talk about that in a second. But notice that shared memory is what I'd call implicit communication, because the only way the communication happens is by reading or writing the shared address. And what's the problem with implicit communication is you don't really know when it's done. All right, leading to the need for synchronization. So the reason synchronization is so important in shared memory is because you don't know when somebody has written a value to you. I don't know. They were going to compute, my favorite number, if you hadn't figured this out already, is pi. They were going to compute the 23rd digit of pi and hand it back to me. I don't know if they're done yet. I suppose if I put a 0 there and I looked and it was no longer 0, I'd have a 1 in 10 chance of being right that they were done. But something's got to happen there, and that's actually, I would say, where shared memory, in addition to being hard to implement well, starts getting really complicated when you got to worry about, did I get my synchronization right? And you'll get ample opportunity to worry about synchronization in later parts of this class. But so let's go back to our little simple program here, and let's suppose we have a small number of processors, which is very much less than the total number of elements in A, and it's all attached to single memory. And so as a decomposition, we could split this up into a set of parallel tasks, each of which compute a part of this. And so we could assign sort of n over p numbers to each of the processors and compute p partial sums and then add those up. Okay? And so here we go. Here's A, and there's only 4 processors. Each processor does a chunk of A, computes f of A, sums it up, and produces these green partial results. Okay, and what you can see here is there's a logically shared things are, for instance, the original numbers and the global sum. Private things are stacks, the individual function evaluations. All that stuff could be kept entirely private to the processor and not shared with the other processors. Okay, now what about the individual partial sums? Well, clearly somebody in the system is going to need to read these to sum them together. Okay, so there's clearly the output of this has some global aspect to it too. Okay, so here's code. 2 threads. Okay, I start with a static integer s equals 0. And this thread goes from 0 to n over 2 minus 1, and it does the sum. And this one goes from n over 2 to n minus 1 and does the sum. And boy, that was easy to write. Does this work? This looks good. Remember, I'm not very far out of my comfort zone. Gee, that's great. Except there's a race condition on s, right? This guy's updating s. This guy's updating s. Chaos ensues. S is wrong. Okay? So a race condition or a data race occurs when 2 processors or 2 threads access the same variable and at least one does a write. The accesses are concurrent, and so it could happen simultaneously. And so we certainly have this problem with a race on S and no clue that this is definitely not going to give the right answer. I can guarantee that. Okay? So let's look here just so you are really, I want to hammer this home. So here we have 2 threads and 2 elements. And notice what happens. Thread 1 runs along here, and we're going to look at this. So we're basically going to square this. So 9 plus 25, so the answer should be 34. Okay, and let's look what happens when we execute. So first of all, this one computes f of 0, f of a of 0, which is 3, gives me 9. This one computes 25, so so far so good. This one reads s and gets 0. This one reads s and gets 0. This one, maybe this guy has a cache miss, so this one goes ahead and adds 0 and 25, gets 25, and stores back 25 into s. This one, meanwhile, adds 0 and 9 and gets 9 and stores back 9. And what do we have as an answer? 9. Okay, so if you ever write a program with data races in there, you better be careful because you're going to get some weird answers to it. Okay? And the question here is kind of what's atomic, and in this particular case, I've sort of assumed that the atomic operations are reads and writes, and you know, we never see half of a number, but the problem is that the atomic thing we actually need is a greater chunk here. We need this s equal reg 1 plus reg 0, reg 1 to s. That needs to be atomic. Okay, and it isn't, because we only have loads and stores so far. Okay, and as a result, we don't get a good answer out. Okay, now here is another option. Notice how I keep a local variable s1 and s2, and this guy goes through and computes a partial sum s1, and this computes a partial sum s2, and we add the results together. Well, it's better. Okay, this one is more likely to give you the right answer. It's still got a race, though. Okay. And this is actually a good deep composition because most of the time we don't require any communication. We really are working on our own stuff, and it's just at the end that we have to make this work. And what can we do? We can put locks around it. Okay, so this is an example where the way we fix the synchronization problem is we make this s equal s plus local s1 an atomic operation by putting a lock around it. Okay, and that is the beginning of the synchronization black hole that you can get into with shared memory, but I just wanted to make sure you realize that you need to do it. Okay, just because I can easily read and write from a location doesn't mean I can easily write a parallel program. Okay, and you will hear plenty, you'll do plenty of synchronization in your labs, and you'll hear about it throughout the rest of the class here. Okay, questions? Now, caching, I argued, I think, previously, is probably a good thing. Probably, right? You need it. Without caching, we lose. What happens with multiple processors and caches? Well, notice here, I've got my big shared memory, which is some memory in the sky, although I guess this is somewhere else now. And then we have are processors, and each of them have their local caches. Okay? And we really need the caches to get high performance because DRAM is slow, and it's probably even slower because it's behind this bus now. It is even slower. And so what happens here? Well, we can suddenly have these caches be out of date with each other and get the wrong answer. Okay, so the caches are good because they reduce the average latency, but, and we can use normal uniprocessor mechanisms, reads and stores and loads to actually access things. But now imagine that I read a value, I store it, an updated value, but it's only in the cache, not in memory, and processor N here goes to read it, and now we've got an inconsistent result. Okay, and I can show you this a little bit clearer here. So here we have a variable u in memory that's the value 5. Processor 1 loads u into its cache, and so it says u is 5. Processor 3 loads u, it says u is 5, but then processor 3 updates and u is 7. And now what? What happens when processor 1 goes to read u? What's it get? Well, according to this diagram, it gets back 5. Why? Because 5 is in the cache. Everybody see that problem? And furthermore, what is it that processor 2 gets? How many people think processor 2 gets 5? Okay, how many people think processor 2 gets 7? How many people think it depends? So it depends because processor 3 could easily have kicked this u equals 7 out of its cache, and so maybe u equals 7 got written back to memory before processor 2 read it. Okay, so this is the beginnings of the cache coherence black hole. Okay, so in order to make shared memory work well, you need to figure out how to solve this problem, and of course, there are plenty of ways to fix this problem. Okay, I'm not going to claim that it's unfixable. Like, for instance, every time I do an update, I send an invalidation across the bus so that all of the other copies are invalidated, and I make sure it gets written back to memory. Okay, so you can imagine arranging so that updates keep your caches coherent. All right, and in fact, the bus idea here works really well because the bus is a broadcast media, but it's hard to scale beyond about 64 processors. And so what people actually do is they do something like directory coherence, which I'm not going to go into in detail, but keep this in mind. What happens is every cache line has a directory associated with it, which is a vector of bits that keeps track of which processor has a copy. And so then before you write, you go to everybody who's got a copy, ask them to invalidate, and when they say, okay, it's no longer in my cache, then you write. Okay? And you do this in hardware. All right? And you can do this easily. I've built machines like this. It's not like it's impossible to do, but it's a level of complexity involved in making shared memory work well. Okay? And you'll hear people from Intel occasionally say, well, cache coherence is too expensive to implement both from a power and from a transistor standpoint, and therefore we're not going to do it anymore, or we're hoping that in the future we won't do it. And then other people will say, well, that's ridiculous, everybody needs cache coherence, and then you'll get, a good argument over beer or something. But keep in mind that making cache coherence work well does require some work. Okay. And then the other thing that I wanted to point out, just so you know, is take a look here. What happens here? We've got, assume that A and flag is 0 to start with, and this processor says A equals 1, flag equals 1, and this processor says, well, flag equals 0, spin, notice the semicolon there, and then when flag is no longer 0, we exit and we print A. And so what does processor 2 print? How many people think it should print 1? Well, you'd like it to print 1, right? Doesn't that seem the intuition? Because this guy is spinning until flag equals 1, and at the point that flag equals 1, A equals 1, and therefore we print out 1. The bottom line, though, is that that actually is not guaranteed by coherence. So the simple idea that everybody sees a single coherent location doesn't make this work, because this is about the relationship between A and flag. And there's something different that can happen, and I actually have a little scenario I won't go through in detail here, but you can imagine that the update to A is stored in processor 2's memory in a distributed memory situation, and the flag is stored in processor 3, and processor 3 gets the flag before the update goes to processor 2, and poof, we got a mess. Okay, so that's cache consistency problem, not coherence problem. And somebody needs to solve that. And what is the memory consistency model? This specifies constraints on the order in which memory operations can appear to execute with respect to one another. And without it, you can't tell much about how the program operates. And it's basically a contract between the program and the system. I want to show you the simplest idea called sequential consistency, which is the gold standard against which everything else is measured. And there was this paper by Lamport that says a multiprocessor is sequentially consistent if the result of any execution is the same as if the operations of all the processors were executed in some sequential order and the operations of each individual processor appear in the sequence in the order specified by its program. You guys are all intuitively got that figured out now, right? The bottom line with sequential consistency is it's a model that actually hits with the intuitions that this should work. And the way to look at this is the following. Here are two processor executions. What I'm showing is every instruction has a forward order that the programmer stated, and values kind of go, here I'm storing 6 into A, and I'm loading that 6 from A. And what sequential consistency says is, anytime you make a run like this, you can reorder via topological sort into a serial order as if this ran on a uniprocessor. Okay, so the sequential consistency gold standard is this ought to look like a uniprocessor run. And what you'll find is there's arguments about is it hard to do sequential consistency or not, and you'll see that a lot of people have given up on sequential consistency, but they need to make sure that you can still program this thing, and that gets a little interesting. So there are, you've probably heard them, right? Sequential consistency, relaxed consistency. There's a processor consistency. There's a bunch of consistencies, and those are really about what do you expect two locations to behave relative to one another when you're programming. Okay, and most things that aren't sequential consistency do not support this style of synchronization. So do not fall into this trap until you've verified what sort of synchronization you actually have available. Okay. And then finally, there's lots of synchronization options. I want to talk a little bit about what's in POSIX threads. So we've got, for instance, mutexes, which are locks, which you can create. So you can create a lock, and you can up here, and then you can lock and unlock. Okay, those are available in POSIX threads, and then you can destroy the mutex when you're done. Okay. Other things. What's the problem with locks? Well, locks can be used incorrectly. So notice, acquire the lock, do an operation, release the lock, increment temp, acquire the lock, store temp back, release. Does this work? No, I haven't made an atomic operation over the load, add, store. Okay, so just because you can use locks doesn't mean you ought to put them everywhere, because you might actually make your program incorrect. Okay, this is all the scare you straight stuff about locks, and then you have to figure out how to use them correctly later. Okay. And the last thing is locks can lead to deadlocks. So notice this: thread A grabs lock A, and then lock B. Thread 1 grabs lock A and lock B. Thread 2 grabs lock B and then lock A. If we happen to be running concurrently such that thread 1 gets lock A and thread 2 gets lock B, we're now deadlocked, because neither of them are going to make it past their second lock. Okay, so it's easy to get deadlocks with locks. All right? Good. So last thing is you can easily, there's barrier synchronization, where this is a very typical thing where you sort of work on a sub, everybody works on something, you hit a barrier, which means everybody waits till everybody's done, then you work on the next thing, and so on. Okay? And in POSIX, there's barriers as well, which you can create, and then you can use them. And you'll learn how to use this stuff in your programming classes. What I wanted to show you here is you can imagine that you could put so many locks in that you don't get good performance. And so, for instance, here's an example where I do that, barrier, 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 versus something that does arbitrarily fine-grained locks. and you can actually do the same operation in much less time with the right locking. And so always keep locking in mind. You know, are your locks holding you up or not? Okay. Now, the final thing, I can skip this for now. So let's talk about message passing. So I talked about shared memory. So message passing is a different programming paradigm. So here, every processor kind of has its own local memory, and there's an arbitrary network, but there's no shared pot of memory in the sky. Okay? And so you could say the program consists of named processes, often fixed at program startup time, and any logically shared data is actually partitioned over processes in different processors, and the only way to share data is by explicitly sending messages. Here's my data. Get my data back. Okay, now those of you who have done any programming in TCP/IP or over the net or whatever, that's the model you got, right? You got to open a socket and send it to somebody. Okay, in a parallel machine that does message passing, it's the same model, but you're at a much finer grain and your messages are faster. Okay? So for instance, here's a case where this processor does a send, somebody else does a receive, and now he can use the data. So explicit send and receive operations. So if we look here, suppose that we had processor 1 sort of has a value, A of 1, tries to send X local to processor 2, receives value from processor 2 X remote, and sums the result. This guy does the opposite, and the goal is each processor has a value. We want to exchange the values, create the sum on each processor in parallel. We're duplicating work here. So what could happen here? Well, depending on your underlying network, if it's like the telephone system, you actually have to get a receive going before the send can complete. And so this send could block, and this send could block, and you could be stuck. On the other hand, if your network does queuing, you could do send, send, they're in the network, receive, receive, and we're good to go. Okay, so, and here's sort of the opposite where I pair a send and a receive with each other. So there's a lot of research out there on what messages look like and what hardware support for messages are there. So for instance, MPI is one standard that's it's a de facto standard. And here's an example where I put together a buffer and I do an MPI send to somebody else, and I have to say who to send it to, and on receive, I grab it from somebody else and I'm good to go. So you're explicitly using send and receive operations to package up data and send it. Okay? No shared memory. Do you need synchronization with message passing? How many people think you need no synchronization with message passing? How many people think you need less synchronization with message passing? How many people think you need synchronization with message passing? All right, so I loaded that question. The question might be, what do I mean by synchronization? The important thing to note here is with messages, that's explicit communication. Remember how I said shared memory is implicit? Message passing is explicit in the sense that the arrival of a message is like a synchronization event. It's data plus the existence of that data. So you can almost argue that you don't need synchronization operations over and above the messages because the messages are themselves the synchronization ops. Okay, now if you were thinking at a higher level of a programmer using a library, then maybe all of the message passing's hidden from you and somebody made it look like shared memory to you, and then all the messages are automatic underneath, and you have to use a synchronization op, which turns into messages. Okay, so that could be the way you answer the question the other way. But the way I like you to think about messages here is they're explicit, and the synchronization is part of the message. So details, data has to worry about where all the data is, what processors is it on. Message passing has it's a higher software overhead than shared memory. Why? Well, shared memory, I do a store. Message passing, I take the message, I possibly have to rearrange it to be a network standard order. If I'm going across processors, I have to marshal it into a message, I have to put headers on the message, I have to send the message. The other side, then we'll have to receive the message, unpack it into structures, and use it. Shared memory, store, load. So you see that from one standpoint, you could say that message passing has a lot of more overhead than shared memory. But from another, you could say, well, in the message passing case, the synchronization is a lot clearer. I know where all my data is. Okay? So the last thing I wanted to mention about messages is the message passing abstraction called active messages is one that's been used to great efficiency in the world. And the idea here is that in a message that you're sending, there's actually a handler address, which is something to run at the other side. And you send it off, and when that message gets received, what happens is the address is extracted and a routine is run as a result of the message arrival. That's called an active message. Okay, and that's basically just a software abstraction on top of messaging. Okay, and lots of message passing possibilities here. You could actually have a separate message processor. So this processor hands messages to this one, and that one handles the queues and the message sends. You could have something like Alewife, which is a machine I built many moons ago, where there's a special send and receive registers in the processor. And the way you send a message is you store a couple of things and you execute a send instruction. And on the receive side, you just look until there's something there, or you receive an interrupt, and you pull the results out of registers. So if you think about it, this option here, perhaps you got a system call, and this processor goes through a lot of work to get the message over here, and then you got to do a system call to get out. That could be a high overhead message system, whereas in Alewife, you execute a couple instructions, it gets sent, you execute a couple instructions, it gets received. And so the overhead of messaging varies a lot based on what the architecture support is. A lot. Okay. And of course, message passing has deadlock problems as well. So here's a case where what I always do is I read a message off the network and I send a response. Kind of like a, request response. You can get in a situation where I can't pull a message off the network because I can't send a result because the network's all tied up. And there on this side, you can't pull a message off because you can't send a result, and you end up with a loop through the network, and now you've got deadlock because of the messages you're sending. Okay, and so a lot of machines get by this by having multiple networks so that you don't get in deadlock problems. Okay, so which is better, shared memory or message passing? Depends. Don't you love all the definitive things I'm telling you today? Both are communication Turing complete. How's that for bad terminology? I mean, you can build shared memory out of message passing. You can build message passing out of shared memory. How do you do that? Well, shared memory is a bunch of requests and invalidates. So the way you do shared memory is you send messages underneath. And you hide that abstraction up high. How do you build message passing out of shared memory? You use FIFO queues in shared memory. Okay, so they're communication Turing complete. The question is really more about what's more natural for the program and what's more natural for the hardware. Okay, so advantages of shared memory is the implicit communication is extremely fast, very low overhead if you go through the cache. Disadvantages are it's very complex to build a good shared memory in hardware, which I kind of gave you an idea. Requires synchronization ops, which is complicated to get right. It's hard to control data caching because the caching happens on demand. If I happen to load something, then the data happens to be near me. Whether that's good for my next operation is hard to say. Advantages of message passing. Explicit communication. I know when I'm sending and receiving something, and I know exactly where the data is, so the data placement's good. Disadvantages. Message passing overhead can be high, it's more complicated to program, and introduces questions of, how do you receive? Do you have to get interrupts or polling? Okay. Questions? The reason I go, yeah, go ahead. I know, we're getting close. Okay. Yes? Oh, is there a question from the?
Yes, but that's the end.
Okay. So we did what I suspected. We ran out of time for the zoo, but what I want to do is I want to show you a couple of interesting things here. So multiple instruction, if you guys will give me 5 minutes. Multiple instruction, multiple data machines, or MIMD, is probably the most common multi-core architecture you're going to run into today. And they have shared memory in many cases, or message passing. These are both options. But the idea here is every processor is working individually and has its own instruction stream. Okay? And for most machines, shared memory is built on top of a message passing network. If they have a bus, that's an exception, but there are a less number of those these days. So here's an example of a symmetric multiprocessor where you have a bunch of processors in a bus in memory. This was very common architecture 15 years ago. It was also very common in the early days of multicore, where there was essentially an on-chip bus. Okay. Here's an example of a distributed memory machine where every processor has a chunk of the memory. And there's typically a mesh network or some low-dimensional network tying them together. And as you can imagine here, there's probably a cache coherence protocol that has to be directory-based or something to keep track of who's got what copies of what data to give you shared memory out of this. Making message passing out of a machine like this is easy. Okay. And then finally, of course, clusters and the cloud and all that sort of stuff are also parallel machines, okay, where they're message passing and you use something like TCP/IP as your substrate for the messages. Okay, and of course you can build a pseudo shared memory on top of that, and there's lots of tools for that so that the programmer can think they're using shared memory. Okay. So I wanted to show you, let's see, a couple of interesting, so here's the SGI Origin is one of the more interesting directory-based machines, one of the first ones, and it actually had full directory-based cache coherence early on. Here's a machine I built. Let's see, I wanted to show you. Here is my favorite message passing machine from the last decade. This is the Jelly Bean machine built at MIT. And what was interesting about this is it had 64 processors on a board, and then boards were put in stacks. And so there was three-dimensional communication on this, and this one is 1,024 processors. And the reason it had this kind of rocket launcher look was so that the boards could be put down, and then they kind of got cranked up into their position, which was kind of fun. Blue Gene is another parallel system. Here's some multicore. I showed you this earlier. Here's an AMD equivalent. So AMD was going off the non-binary number of processors for a while. Now Intel's off on that direction. Something about 6 processors. It just sort of grates you the wrong way if you're an architect, but oh well. Here was Niagara, which was a machine that didn't have a lot of beefy processors like the previous two, but this was from Sun Microsystems. This was targeted at explicit multi-threading. So there were 8 threads that could be running in the pipeline, and you didn't get full performance unless you had all 8 threads running in the pipeline. Okay. And let's see what else. Oh yeah, Cisco was one of the first to actually have lots of processors for routing. IBM Cell had a lot of processors, and then of course there's the GPUs, which I mentioned earlier, and here's an example of one of the latest ones, which has lots of processors and lots of CiMD within each processor. And so this is probably one of the more powerful graphic architectures out there today, and I'm sure you'll hear a lot about it later in the class. Okay, so in conclusion, thanks for the 5 minutes here. Uniprocessor parallelism is pipelining superscalar out-of-order execution, vector processing, PseudosimD, GPU, etc. Multi-threading, multiple independent threads executing on the same processor. Talked about memory systems being very important and in fact giving you weird results sometimes if you're not aware of them. And it almost leads to needing auto-tuning. And Jim's going to give an interesting discussion on auto-tuning tomorrow, I think. We talked about the shared memory programming model, which is a pot of stuff in the sky with its own ease of use, but then complexities of getting right under some circumstances. We also talked about message passing, which is an alternative. And I think that's it. So I'm sorry for going over a little bit. I think we had a question from the net.
Yes, so the one question from the internet was, what are the effects of data locality on power?
Oh, the effects of data locality on power. Big deal. So if you have to move data around a lot, it turns out what you end up doing is moving pins around, which causes capacitance to change and causes a lot of power to be used. And so making sure that you're not moving data around when you don't have to is an important part of today's systems, both from a performance standpoint, because moving takes time, but also from a power standpoint. So I'd say data locality and power go hand in hand. Very important. Even getting on and off the DRAM. So I will tell you that the DRAM today in a server system is probably a third of the power. Okay, and that's getting on and off the chip uses a lot of energy. So that says if you can run in cache, you're going to use a lot less power than if you are cache missing all the time. Yes?
That will be a topic of many later talks.
Good. Any other questions? Or yes? Here's a microphone. Why not?
One would think intuitively that debugging these systems is an order of magnitude more difficult than the old uniprocessor system. I wonder, have there been useful tools developed that will make them, easier to debug?
Debugging these systems are 2 orders of magnitude more complicated than, so clearly this is much more complicated to debug these kind of programs. There's a lot of interesting correctness tools that people have brought forward. So I showed you data races in my simple shared memory example. So there are tools in the PARLAB and other places that analyze programs and look for data races, because if you got a data race, which is a write and a read unsynchronized in some program, it's likely there's a bug hidden there. So certainly those kind of analysis tools people have been working on quite a bit. There are, but yeah, let's face it, parallel programming is more complicated. The one thing I will finish on that is the way that you make parallel programming less complicated is you don't program in parallel. What do I mean by that is if you were to actually, in fact, you'll hear more about this in the rest of the course, one of the takes that the PARLAB has done is decomposing operations into these natural patterns, or dwarfs, as were mentioned, which are these common patterns that people use a lot. And the idea is that you as a programmer are decomposing into these common operations, sparse matrix, multiply, whatever. And you don't worry about how it's done, but just that you want to do that. And somebody who's been working at this a lot longer than you have is implementing those operations for you and doing all the parallel work. And so by working at the pattern level, where you're expressing things as patterns that are more natural to you, rather than programming in parallel with individual locks and so on, that's another way to get by the correctness. So that's another take that the PARLAB's doing. Yes?
We will have 2 lectures on correctness tools and debugging tools during the lecture. One on the correctness of the behavior and the other on performance debugging. So stay tuned.
Yeah, performance. Yeah, even worse than getting it correct is, does it perform well, and why does it not perform well? Maybe the better question. So, all right, I think we're done with questions.
I just wanted to say a word, word about lunch.
Yes, go ahead.
Last question.
Last question here. Microphone.
Thank you. Just curious, from all this work that has been done, have you been able to come up with an architecture or a suite of architectures and implement them in FPGAs to come up with an optimal set of computer architectures for parallel programming? You have a lot of insight we were seeing today.
Sure.
So has that been mapped into hardware?
So I would say I give you 2, there's a lot of parts to your question. I give you 2 quick answers to that. One, I think it's pretty clear that not every architecture is good for every application. This GPU-CPU split is an interesting one that almost seems like it's going to be around for a while, because those are very different classes of applications. I know there are colleagues of mine that would disagree a lot, but the other, so there isn't one architecture.
But FPGAs allow you to reconfigure.
Sure. So the second question you mentioned about FPGAs is I don't think there's as much work that we're doing in on-the-fly reconfiguration for architectures. Other people have done that. What we are doing with FPGAs is different, and in a different way of using them. We're using FPGAs to emulate new architectures to sort of figure out what the right one is, but it's not as, the FPGA in that case is not the computational engine, but rather an emulation engine. But yeah, it could be too. So you bring up a really good point. I mean, that's just, we aren't doing that much work in the PARLAB, but there's been a lot of work in Berkeley on using FPGAs as computation and compiling directly to FPGAs. There was work, John Worsnick did some work like that a decade ago, and there's been a lot of good work like that. That's just not something that we've been doing recently.
So a lot of our colleagues in industry believe the future will be heterogeneous, so that's
Yes.
part of it. So
yeah, heterogeneity is the future, I think.
So, and speaking of heterogeneity, let me just talk about your lunch choices, because there are quite a few. In fact, if you just walk across the street, the choices of cuisines you have include Chinese, Thai, Vietnamese, Korean, Japanese, and hot dogs. And there are even more choices just around the corner.
The hot dogs are good, by the way.
Yeah, they're excellent. So depending on what you want to eat, there's many choices, and we'll see you back at 1:15. Thank you very much.